regarding the subject of irrigation engineering, we are going to have the quick revision program regarding irrigation engineering. As you know, first one is storage works. Second one is diversion works. Third one is distribution works. Fourth one is utilization works. The total syllabus, around 12 chapters, will be regrouped under these 4 major headings. In storage works, we got gravity dams, spillways, and energy dissipators. In diversion works, we got river training works, it is mainly meant for ESC examination. For GATE, it is not so important. And diversion headworks. In diversion headworks, both weirs and barrages, theories of seepage in a highly permeable soil, the 3 theories we discuss. Under distribution work, we got lined canals, we got the design of unlined canals, and we got the canal regulation works. Canal regulation works. Under the utilization works, first chapter, basics of water resources engineering, that is nothing but the methods of irrigation, soil, water and plant, water requirement of crops, and quality of irrigation water. Quality of irrigation water. These subtopics we are having as chapters. As we know, even though the water travels from reservoir to the field, our journey of study of irrigation engineering, quick revision program, will start from the utilization works, distribution work, diversion work, and finally storage works. Our movement will go like this. So, you can start from here also, but generally in the material it is given like that, and also in the standard way of coverage of the syllabus can be done, starting from methods of irrigation. We will see. So, first one, the 4th unit we are considering under utilization works. Under utilization works, we got methods of irrigation, methods of irrigation you must know. Regarding the soil-water plant relationships, some practice you must make. Most important part of this first unit, water requirement of crops. For ESC examination, these three are for GATE and ESC. Only for ESC examination, for GATE it is not much considerable. Quality of irrigation water. Quality of irrigation water. Let us see what are the various methods of irrigation you must know. When you know the types of irrigation, first one is the flow irrigation. Second one is lift irrigation. They may give the entire definition and ask what is that type of irrigation or what is the difference between flow irrigation and lift irrigation. Such questions may be asked. As you know pretty well, flow irrigation is nothing but supply of water from the source to the fields by the water movement taken place by gravity. So here water movement will take place by gravity. Source is at higher elevation, field is at lower elevation, water comes by gravity very easily. No much expenditure is needed, no special works are needed. We can continue with the problem very easily. Lift irrigation. Source is available at lower elevation. We have to lift the water by some external mechanical agency. Then the water will come to the greater elevation, then transferred to the field. So if the source is at lower elevation and the destination is at higher elevation, we have to do work against gravity, some expenditure, some external mechanical or electrical source of energy must be there, like a motor and pump. So lift irrigation, flow of water that will take place against gravity. You can see the specialty of lift irrigation. Flow irrigation, lift irrigation. It is a very cheaper one, it is a costly one. Because whenever we are making work to get the water riser from low elevation to high elevation, amount of energy you have to spend and the corresponding money expenditure also will take place. So this is the one important classification they may ask. Second one is systems of irrigation. In systems of irrigation, we can say perennial system. Water is supplied throughout the field. Water is supplied to the field throughout the year, throughout the base period. Whenever you require, in whatever quantities of your requirement, water can be delivered to the field. That is perennial irrigation. Perennial means continuous, non-stop. Second one is non-perennial irrigation. Non-perennial. There is flood in the canal or river for about 1 week to 10 days. During those 10 days, we supply the water in abundance to the soil. We don't get the guarantee next time when we are going to supply the water. Quantity is fixed here, number of times of water supply is fixed here. Quantity is not fixed here, number of times of water supply is not fixed. Time duration between two consecutive waterings we cannot decide in case of non-perennial irrigation. Non-perennial irrigation is also called flood irrigation. Is also called flood irrigation. One more classification. Direct irrigation system and indirect irrigation system. What is a direct and indirect irrigation system? From the source directly, if the water is getting to the fields, we are not having any reservoirs. We are just providing the weirs or barrages to get the water diverted from the source to the fields. No storage works are needed in direct irrigation system. No storage works. In the case of indirect irrigation system, appropriate storage works and works of disposal called spillways and proper energy dissipators, everything is needed in the indirect irrigation system. Combining these direct and irrigation systems, we got a system called Bandara irrigation. Bandara irrigation. This is regarding systems of irrigation. When you see the methods, everyone knows the important question that can be asked in this particular subtopic is only on the methods of irrigation. Methods of irrigation. There are three methods of irrigation: surface irrigation, subsurface irrigation, and sprinkler irrigation. Surface irrigation, subsurface irrigation, sprinkler irrigation. Generally, question will be asked on surface irrigation. What are the situations when we should go for sprinkler irrigation is also a previous question in ESC examination and also once in GATE examination. So in surface irrigation, if you remember correctly, there are three methods. First one is flood the land with water. Second one is provide furrows within the field. Furrow is a small open channel provided inside the field so that from that furrow water will be traveling below the ground level at the root zone level. Water will be taken by each and every plant from the furrow. Furrow is open to atmosphere. Furrow is a small stream of water provided within the field in furrows. Furrow, an open channel provided in the field throughout the length of the field where water is exposed to atmosphere openly but supplied to the plants at the roots level. At the root zone level, water will be supplied. That is called furrow irrigation. And the third method we are having is contour farming. Contour farming. In the subsurface irrigation, we got mechanical and non-mechanical methods of irrigation. We can get drip irrigation and trickle irrigation. Drip and trickle irrigation with a slight difference. Extension throughout the area by infinite series and a parallel combination of PVC pipelines is trickle irrigation. Individual connection of the PVC pipelines to the individual plants by drip irrigation. So the more advantageously trickle irrigation is provided. So if you go for subsurface irrigation, you prefer only trickle irrigation. Please understand this. Contour farming, when we want to have the irrigation of the crops like tea, coffee, ilachi, corundum, etc., clove, etc., you have to get them cropped in the hilly areas. We supply the water at the highest elevation. Water will be coming by gravity to the bottom, covering the entire surface area of the field being irrigated. So, contour farming, you can say alternate name, hilly irrigation. Furrow irrigation, I told you, if it is the field, here we provide furrows, water will be there. At the root zone level, water will be supplied to all plants. So, the entire area will get uniform supply of water. Furrow, an open channel provided in the field with the water flow open to atmosphere and supply of water to the plants at the root zone level, that is called furrow irrigation. Flooding, as you know pretty well, if you go on supplying the water without calculation, that is called wild flooding. Wild flooding is also called uncontrolled flooding. Uncontrolled flooding is not advantageous. We should avoid uncontrolled flooding. So we got flood, controlled flooding. The meaning of controlled flooding is quantity of water being supplied to the field will remain constant. In controlled flooding, we got free flooding, free field flooding, check flooding, levee flooding, cross contour flooding, basin flooding, and border strip flooding. 70% of the Indian irrigation system, like rice, wheat, maize, jawar, etc., will get irrigated by check flooding. Check flooding, we supply the water through the nozzles and it will be touching the surface flooding only. It will be entering into the field. From there, we have the laterals and sublaterals. We are going to get the supply of the water throughout the field in the most effective way, and water flows by gravity only, and that is check flooding. Most common method. If you want to irrigate orchards, mango orchards, etc., then we are going for basin flooding. If the water is supplied by long strips, two or more number of connections are made to the field, long parallel strips, that is called border strip flooding. In border strip flooding is the most common one. Most common method of irrigation. Most common method of irrigation. Border strip flooding is also effective method of most effective method of irrigation is border flooding. This is for orchards. Levee flooding is not much advisable. In our house yards, free field flooding for small areas when we want to irrigate with vegetables and flowers in small area combinedly at a time, that is called free field flooding. So majority of all the methods of irrigation, most common is check flooding, rice, vegetables, wheat, all the things we can keep. So remember the two names, check flooding and border strip flooding, both are important in this particular subtopic. Here we got, then previous one is sprinkler irrigation. When do you go for sprinkler irrigation? That point also you must remember. When the area is of water scarcity. If the water is suffering from water scarcity, we don't prefer scarcity. We don't prefer wasting the water supplying to the soil. We don't prefer it. So when the area is of water scarcity, there is no other method but going for sprinkler irrigation. Then hot and arid zones. hot and arid zones. When the soil has less porosity, high permeability. When there is no soil has got bad drainage density, we can get the more and more water stocked in the soil, so that the dangerous again gets waterlogged. So sprinkler irrigation is provided in any one of the four situations: areas of water scarcity, high temperature zones, when the soil has got less porosity and more permeability, water cannot stay if you on the surface, so surface and subsurface not useful, directly supply the water to the plants, that is sprinkler irrigation. Regarding the sprinkler irrigation, formula for discharge to be supplied is equal to Sx into Sy into V. Sx is the spacing in x direction, spacing of the sprinklers in x direction. Sy is the spacing of the sprinklers in y direction. V is the velocity of water getting ejected. Velocity of the water getting ejected. If n is the total number of sprinklers, capital Q is equal to n into small q. This is the discharge per unit width. Multiply with the number of discharges, you are able to get the total discharge delivered. In the units of meter cube per second, we can understand very easily. If you go for border strip irrigation, water will be supplied like this. A is the area of each strip. F is the rate of infiltration of the supplied water to the soil. Y is the depth of the water stored. T is the time of water supply. The present topic is how much time is required to irrigate a given field by this border strip irrigation. So we are applying the formula Q into dt is the volume. Q into dt is equal to F into A into dt plus Y into dA. Y is the depth of the water stored externally. F is the rate of infiltration. Q is the rate of water supplied. A is the area of each border strip. You can get the time required. If you don't want to waste for surface storage, then y value becomes 0. In this equation, if y becomes 0, dt gets cancelled. dt gets cancelled. Then you can get A max is equal to Q divided by F. Rate of supply of water divided by rate of infiltration. Rate of supply of water divided by rate of infiltration. This was the regarding the methods of irrigation. Dear friends, let us remember these two formulas. In the border strip irrigation, T is equal to Y by F log Q divided by Q minus FA. This is if we want to irrigate supplying water Q to the area A. Y is the external storage, F is the rate of infiltration. How much time it takes to get the water supplied to the field? That is the formula given. If you want to have the optimum utilization of the water, you need not make the water to stay in the field. Y value will become 0 automatically. What maximum area I can irrigate? The maximum area simply Q upon F, that is rate of supply divided by rate of infiltration. Rate of supply of water divided by rate of infiltration. So many hectares or square kilometers, I can get the maximum area that can be irrigated. I repeat, if you don't make the water to stay in the field externally, y value is 0. In the differential equation, if YdA is equal to 0, you are able to get the value very easily. Friends, this is regarding methods of irrigation. When I say the word soil water plant, of all soils, loamy soil is best. Next best is clay. Next best is somewhat silt and sand. Other soils are not at all useful for irrigation. Loam, clay, silt and sand. Best one is loam. If you are able to take the irrigation of the loamy soil, sand, silt and clay are having around 30-35% of the total volume, then you can say there's a loamy soil is an ideal soil which has got good storage capacity and drainage capacity. If somebody asks you what type of soil is preferable, your answer must be good N and good K. High porosity and high permeability. That means able to store the necessary water, able to dispose of the surplus water. If the soil is able to have the properties on its own, that is the better soil. So, if somebody asks you what soil is best, the loamy soil is best. In such a loamy soil, when we supply water, the moisture content of the soil goes on increasing. You should never supply the water beyond field capacity. You have studied in the regular course also. So, the maximum moisture content we can deliver to the field in a particular soil is nothing but its field capacity. So, to explain about the field capacity and other moisture contents, you must know about the pores, micropores and macropores. Micropores and macropores, these are called CP. Capillary pores, these are nothing but non-capillary pores. The pores which are physically visible, smallest very in size, they are called capillary pores. Capillary pores are able to store the water, and macro pores will have the storage of air. Thus, for any irrigation system to start with, soil must exist as a three-phase system. Do remember, to start the process of irrigation, to start the process of irrigation, soil must exist as a three-phase system. Soil must exist as a three-phase system. Soil must be there, water must be there, and air must be there. Sufficient water and sufficient air sufficient air is necessary to make the soil bacteria active. If the soil bacteria is active, they can deliver the nutrients to the plants within the soil. The nutrients will be available primary, secondary, and tertiary. The nutrients can be delivered to the plants by soil bacteria, which will become very active in the presence of air. So, a minimum percentage of the volume of the soil should be occupied by air, which is essential for growth of the crop. Water for all the evapotranspiration and other needs. Evapotranspiration, metabolic action, growth of the crop, sharing of the water between the surrounding soil particles. To serve all these purposes, amount of water is needed. So remember, water is very essential. Air is also essential. Duty of air is to deliver the nutrients to the crop. To deliver the nutrients to the crop, keep in mind always a soil must exist as a three-phase system if it has to continue as a suitable soil for irrigation. Water is needed to meet consumptive use. Everyone knows what is the consumptive use of the crop. It's the daily water demand of the crop to meet for evaporation, transpiration like process. So, all capillary pores, that is micropores, should be filled with water. The roots of the plants are able to take the water by capillary action. Capillary pores should have the storage of the water. Non-capillary pores should have the storage of air. All CP filled with, so once we fill with NCP with air, it will remain as it is. Unless otherwise we supply more water. Water density 1000 kg per meter cube, air density 1.24 kg per meter cube. If we supply more water than the capacity of the capillary pores, the non-capillary pores starts getting filled with water, dislodging air molecules. As a result, the crop growth will be highly damaged. So, any crop, any soil, your CP-NCP combination should properly get filled with water and air. Remember this point. A theory question may be framed in this context. What is meant by consumptive use? It is the daily water demand of the crop. To get the proper vegetative growth every day, on the average, what is the depth of the water required? That is called consumptive use of the crop, denoted by CU. And capillary pores should be filled with water, and CP should be filled with air. Based on that, you know pretty well, when the moisture content is equal to saturation capacity, when the moisture content is equal to the saturation capacity, CP should be filled with water, because saturation capacity and CP also should be filled with water. Crop growth will be highly damaged. Sorry. Define field capacity of the soil. It is the moisture content when which all the CP will be filled with water, all the NCP will be filled with air. That is the most ideal case. Whenever farmer is supplying the water, he should not supply water beyond field capacity. If he supplies water beyond field capacity, area gets waterlogged. Crop output will be highly damaged, either qualitatively or quantitatively. That's why field capacity is important. Define field capacity. It is the unique moment of the soil. It is the unique moisture content of the soil where entire CP filled with water, entire NCP filled with air. Once we store the water in the capillary pores, plants start consuming water. Plants start consuming the water 24/7. water storage in the soil gradually starts decreasing. So the next moisture content is optimum moisture content. There we got air will remain as air only. In this 100% water, only 50% water and 50% air. This is at optimum moisture content. If you still go to the next lower water content, temporary wilting points, only 30% of the water will be available in capillary pores and 70% water totally available, 70% air is totally available inside the soil. The most dangerous one, permanent wilting points. 10% of the water is available in the capillaries. 90% of the air will be available. 50% is already available. Remaining 40% coming from capillary pores. At PWP, at permanent wilting point, soil has got the last 10% of the water which is kept hidden in the soil. That is called hygroscopic water. Any farmer cannot deliver this last 10% of the water to the crop. With that, field will be maintaining for some distance to be alive without getting supplied to the plant's growth and other factors. So if somebody asks you, define field permanent wilting point, it is the minimum moisture content of the soil at which the inextractable last 10% of the capillary water is filled with capillary pores. 90% of the non-capillary pores and capillary pores will get filled with air molecules. So you can see this is the last one, of course, ultimate wilting point, where there is no water content at all, ultimate wilting point. So you can see when you take the soil in the permanent wilting point status, go on adding water, moisture content will be going on increasing from 10, 20, 30, 35, 40, 45, 50. So beyond 50 is luck, whether you can solve it or not. You should remember, farmer should never supply water beyond field capacity. Wherever, if you take a graph to explain this, if you know, for example, this is the field capacity, say this is OMC. Once the moisture content comes down to OMC, should supply the water. Again, plant will consume the water for the next 10-15 days. Next 10-15 days. Again supply. Again 10-15 days. Again supply. You can see, as a farmer, your duty is to supply the water from OMC to field capacity. Never supply the water beyond field capacity. Never. Supply of water must be done to the field. Supply of water must be done to the field always from OMC to FC. If we are not able to supply the water at OMC, then the crop output will be a little bit damaged. The more away the starting point of the water supply to the field with reference to the moisture content equal to the value of OMC, then the larger the distance, the greater the influence of the impact of the crop output. So it's always advisable to supply the water to the field when the moisture content equal to OMC. Please remember this. How much water we are going to supply? So depth of the each watering is given by the formula S into D into FC minus OMC. At OMC you have to deliver, up to FC you have to supply. S is the specific gravity of the soil. What is this DW? DW stands for depth of each watering. हर एक बार खेत के लिए फार्मर कितना पानी सप्लाई करना चाहिए था. Its duty is to rise from OMC to FC. As you know pretty well, Y at any moisture content is equal SD into MC. Minimum water available in the soil, is equal SD into UWP, PWP. How much is the minimum depth of the water that will be there in the soil? S into D into PWP. In this, should know the symbols. Everyone knows S is the specific gravity of the soil. Specific gravity of the soil. D is called the root zone depth of the soil. Root zone depth of the soil. Everyone knows what is the root zone depth. If it is the ground level up to 1 to 1.2 meter, 1 to 1.2 meter, the water supplied can be taken by the plants easily. So, what maximum distance through which the water can be sucked and the plant will be survived from the possible depth. So, that is given by D. D is nothing but zone of existence of possible water below the ground level. Root zone depth is generally 1 to 1.2 meter for most of the soils. So, what is this formula? dW first, YMC is equal, Y minimum is equal to SD into PWP. Y maximum is SD into FC. So, Y optimum is equal to SD into OMC. So, how much? What is the depth of each watering to raise the moisture content by the farmer every time? SD into FC minus OMC. So, do remember dW is equal to YFC minus YOMC. How much water I can supply? As I told you, you can see the saturation capacity, field capacity, OMC, TWP, PWP, last one is UWP. Every time I will be supplying the water between OMC and FC. After 10-15 days, all the water supplied will be consumed by the plant. Again, it will come back to OMC. Water is not available, may come down. What is not possible may come down. There, the farmer should be able to get the water delivered. Again, it is coming back to FC. There is no rule that always water will be supplied from OMC only. Availability of water may be there in the field, or I am just giving you the synopsis of soil, water and plant. 6 moisture contents, saturation capacity, field capacity, optimum moisture content, temporary wilting point, permanent wilting point, ultimate wilting point. So, at any possible moisture content, what is the water available? So, formula SD into MC. YMC is equal to SD into MC. Suppose somebody asks you, in a soil of specific gravity 2.5, root zone depth 120 centimeter, 15% moisture content must exist, and the PWP is 5%. So, how much water you have to supply? Depth of the water to be supplied is equal to S into D into MC2 minus MC1. Specific gravity 2.5, it is 120 centimeter, initially 5%, now you want 15, 15 minus 5 by 100. It is 10 by 100 to 2, therefore you have to supply 5 centimeters, because D is in centimeters, 5 centimeters, you have to supply the water. Sorry, this is the 10, 100 will get cancelled, 2.5 into 12, 2.5 into 12, that is 30 centimeter water. If you supply the water 30 centimeter, moisture content of the soil will get increased from 5% to 15%. Say 15% is field capacity. This formula, friends, whether you are writing GATE or ESC examination, this formula, kindly once again concentrate on the formulas. At any moisture content, depth of the water is given by SD into MC. Y minimum taken from the So humidity of the atmosphere is SD into MC minimum. Minimum moisture content, that is nothing but SD into PWP. What is Y minimum practically? SD into MC practically. SD practically is nothing but, MC practically is nothing but starting from PWP. So SD into PWP is the formula for Y minimum practically possible. Fourth formula, what is the depth of each watering? What is the depth of each watering? dW, I told you, SD into FC minus how much? OMC. We are able to calculate the depth of each watering also. What is available moisture? Available moisture. The moisture that can be given to the soil at the maximum. Available moisture AM at the maximum. Highest is FC, minimum is PWP. FC minus PWP. What is readily available moisture? Readily available moisture. Readily available moisture denoted by RAM. RAM is equal to readily available moisture. So FC minus OMC. Readily available moisture is safest zone of water supply without giving any damage to the growth of the crop or any damage to the final crop output. The crop should not get damaged physically. The dam should not, the plant is not able to get the sufficient growth. Then decay is said to be done. Understand? Anyway, you must, because that much time is not there to learn what happens to the crop if you don't supply necessary water, etc. Just understand at what moisture content what will happen to the crop. He may give you a match the following question. He may give a simple theory question. He may give you a numerical problem like this. Sometimes specific gravity may not be given. Sometimes specific gravity may not be given, sir. Specific gravity S is equal to gamma soil by gamma water. Specific weight of soil by specific weight of air is called specific gravity of the soil. Sometimes we don't get this value also. Then we can use the porosity divided by field capacity. Porosity small n, field capacity safest maximum percentage. So porosity by field capacity will give you specific gravity of the soil. S stands for specific gravity of soil. First one is the ratio of specific weights. Second one is the ratio of percentages. Porosity in percentage divided by field capacity in percentage. Kabhi value of gamma soil nahi diya to check for the somewhere in the problem might have given the value of porosity also and also field capacity at OMC. This formula is also important and the DW formula is also important. You are right, mister. Always we cannot bring the soil to a temperature, to a moisture content less than PWP. If we want to get out, if we want to bring out, extract the last 10% of the water, if we want to bring out, that is from PWP to UWP, I should keep that soil in the oven, means oven hotness conditions must be created. So your 104 degrees centigrade, 110 degrees centigrade, that is fine. Only by oven heating, the last 10% of the water, which is called hygroscopic water. I am going to give the 3 types of water, my dear friend. Your statement is correct. In second formula, it must be What is the second formula? We'll see. Yeah, it is UWP. Because UWP for any soil is 0, SD into 0, 0 into SD, therefore 0. Why minimum practically SD into PWP? So that's why we are going to give you saturation capacity, field capacity, OMC, TWP, PWP, UWP. This is if you are supplying the water beyond field capacity, it is dangerous. It is dangerous to the crop. Land will get waterlogged. Crop output will be highly damaged. Your growth of the crop will take place under healthy conditions between FC and OMC with somewhat illness up to TWP. Plant can survive up to PWP. This is the zone with moisture content less than permanent wilting point. This is the last 10% of the capillary water. So saturation capacity to field capacity, it is the surplus water which cannot be stored in the soil. Such a water is called gravitational water. It has to be disposed of from the soil so that plant's growth will be good. Between field capacity and permanent wilting point, up to here most comfortably, up to here most practically, what is the zone of the moisture content in which plant is alive and the crop is growing on well? That is called, that water is called capillary water. From permanent wilting point to ultimate wilting point, last 10% of the water in the capillary pores cannot be extracted. That water cannot be extracted by many means of capillary action, not at all useful for the plant's growth. It is the hidden water in the soil, strongly attached to the soil molecules. This last 10% is called hygroscopic water. So if you want to classify the soil water has got three types. Number one, gravitational water. Number two, capillary water. Number three, hygroscopic water. These three types of waters also you must remember. Which water is has to be essentially disposed of? Answer, gravitational water. Which water is essential for the plant's life? Capillary water. In that more useful field capacity to OMC. That is called RAM. FC to PWP is called AM, available moisture. AM is nothing but capillary water zone. AM is nothing but capillary water zone. So you can get the three types of water, soil waters: gravitational water, capillary water, and hygroscopic water. Hygroscopic water, these three waters we can see. Define, somebody asks in the question paper, GATE or ESC, some total definition is given. What is the answer? The answer may be hygroscopic water. Hygros is the water hidden in the soil, strongly attached to the soil molecules, cannot be taken out, cannot be extracted out, even we apply a pressure of 40 kilopascal on the soil. Available moisture is equal to FC minus PWP. Readily available moisture is equal to FC minus OMC. RAM is equal to 70 to 75% of AM. dW is equal to these formulas you must practice. Y is called water storage capacity. dW by Y is equal to this formula also very important. All these formulas clear. You may get the problem on dW. dW formula, this formula is important. 2-3 times they asked the question on Y value also. He may give the, for example, if you take a problem, the recent year question papers, specific gravity 1.4, D value 100 centimeter, from 10%, moisture content will get increased to 14%. From 10%, we are increasing to 40%. So, what is the depth of watering? SD into MC2 minus MC1. SC is 1.4, it is 100. And MC2 minus MC1, 40% minus 10%. Depth of each watering 42 centimeters. So, these formulas and areas are important for the gate preparation, especially ESE also. They have given so many times the question.